Alrighty, good morning, everyone. So today we're going to start our new chapter, which is dealing with currents and with resistances and all kinds of different stuff here. So first thing to point out before we actually go to this kind of picture here is that we're no longer going to be in electrostatics. So we're now leaving electrostatics and then going into electrodynamics. So basically, statics, of course, means that there was nothing moving. So for this one, we had stationary charges. So this gave us stationary charges, which then created electric fields. So now we're going to be playing with moving charges, i.e. dynamics. And after this exam, we'll talk about what this actually gives us, but this is actually going to give us magnetic fields. But again, we'll come back to this after this particular exam. But that's where we are right now. So now we're translating from electrostatics into electrodynamics. Now, certain things are also going to change. So in electrostatics, what we said is that inside of a conductor, the electric field always had to be equal to what? 0, right? So when we had static charges inside of a conductor, we know the electric field had to be equal to 0. But in this case, since our charges are going to be moving, what makes them move? The electric field, which means that now our electric field will no longer be equal to 0. There has to be an electric field present, otherwise the charged particles would never actually move. Right? So this is going to be a major difference between the two. So in this case, we had to have the electric field equal to 0 because we had static charges, but now we have to have these charges actually moving with some sort of velocity, which means they start off with some sort of acceleration, which means there has to be some sort of electric field. So in this case, there has to be an electric field present. So it is not a contradiction of what we said before. It is just now we're dealing with a different scenario. Okay with this? So this is the mental picture I want you to have in mind as we actually talk about all this stuff. So now this is actually more realistic than what it is that we're going to deal with. So it turns out it's actually negative charges which move, not positive charges, but we're going to pretend that it's positive charges. And this is purely based off convention. So when they originally discovered electricity and currents and all these different things, they thought it was positive charged particles which are moving, basically based from Benjamin Franklin. So we thought it was positive charged particles which would move in this direction. Turns out it's actually negative charges which are going to move in this direction. Ultimately, it doesn't change the current at all. But again, in reality, it's actually negative charges moving in the opposite direction at which the positive charges we say are going to move. But this is the picture we're going to work with. So our picture then is what? First, we have a battery. The point of a battery is, again, to supply a constant potential difference, which is then going to create an electric field. That electric field then is going to try to accelerate these charged particles because the electric field, as we know, is going to create a force onto them. So the force is Q times E, which means these guys are going to try to accelerate. But we have this thing here, which is our resistor, which is then ultimately going to slow them down by making elastic collisions. So these electrons, or we're going to pretend they're positive charges, are going to try to be accelerated across here, but they're going to hit the atoms which are on the inside, which is then going to impart some of their kinetic energy onto these atoms. So inside of the metal, these things are already oscillating, right? Because atoms always oscillate. But as these electrons here, or we're going to pretend positive charges, hit these guys, there's going to be a transfer of kinetic energy, which is going to cause these guys to oscillate with a bigger amplitude. Now, what we also know is what? By kinetic theory from last semester, there we go. So from physics 205, we know that kinetic theory, meaning that the kinetic energy is proportional directly to the temperature. So as these guys oscillate with a greater amplitude, they also have a greater kinetic energy, which means that that's going to manifest itself as heat. Okay, so as these guys oscillate greater, the temperature becomes greater, and then ultimately this thing is going to lose energy by losing thermal energy. It's going to radiate temperature. Right? So as these guys are trying to accelerate across, making these elastic collisions is going to cause them to slow down, bounce backwards, be accelerating in the opposite direction, hit another one, slow down, speed up, slow down, speed up, slow down. until eventually this thing is going to move across the resistor here with a constant velocity, which is going to cause all of the charged particles to move throughout this entire system with a constant velocity. So what we're going to call the drift velocity, which you can think of basically as currents. But we'll come back to that in a second. So, and as we talked about before, the point of the battery is not only to supply this constant potential difference, but it's to have these little angels carry the charged particles from one side to the other side. No, there's no angels, but it's okay. So in this case, again, what we said is that the battery has to do work onto the charged particles to move them across this way. Now, again, these are electrons, so I have to do work onto there because the electrons don't want to go to the negative side. So I have to do work to overcome this Coulombic repulsion to bring them from the positive side to the negative side. So this is the picture that I want you to have in mind. We're going to talk about each one of these elements on the way through. So what actually is current? What is resistance? How does this guy heat up? i.e. power, and all these other things. So first thing to notice is what if I increase the voltage of the battery, what happens to the kinetic energy of these atoms? Well, it massively increases because now I'm creating more collisions, which means getting more kinetic energy, which means it becomes hotter. Okay. Now, if I say turn down the resistance, what happens in that case? It gets even hotter. Right? So this brings up an interesting question. Why do you have a circuit breaker in your house? Why do you have a circuit breaker? What's the point of the circuit breaker? What's that? So it doesn't what? Not exactly explode. Well, kind of explode. But again, if this thing is heating up, what happens to the wires in your house? They also get hot, right? So if they get hot and they get arbitrarily hot, and they're going to be around insulation and other things, what's eventually going to happen? It's going to catch on fire, which means what's going to happen to your house? Odds are it's going to burn down, right? So the point of the circuit breaker is to actually monitor the amount of current which flows through to make sure that the temperature of these things don't exceed a particular temperature threshold. Okay, so for every different part of the house, it requires a different amount of current depending on what it is that you're actually running. So, for example, your dryer versus your dishwasher versus lights in a bedroom versus your microwave, and etc. So what the circuit breaker does is it monitors the amount of current which is flowing through it, and then when your current goes too high, it then basically trips it, kills it, so that way the temperature doesn't go too high and it burns down your house. This is the point of having a circuit breaker. Mm-hmm. But again, as we talk about these things, this is the picture I want you to have in mind. So again, the point of the battery is to create an electric field, which tries to accelerate these particles. The point of the resistor then is to slow them down, as well as radiate away the energy at which it is the battery is supplying to it, which means that there's going to be a power lossage. And again, that power lossage comes from the fact that we're having elastic collisions, increasing the kinetic energy then of the atoms inside of the resistor, causing them to massively increase their temperature, which then gets carried away as radiation. Right? So this guy is adding energy, this guy is losing energy due to this thermal radiation. Okay. And again, this current that moves through here is basically what we call the drift velocity, or it's the average velocity at which these charged particles move through. So the bigger the current, the bigger the velocity at which these guys are moving through. It's a stupidly low velocity, but it's still a higher velocity. And we'll do some examples of this to kind of talk about each one of these things. Okay, so again, as we talk about these things, this is the picture I want you to have. So we're going to talk about all of the different ingredients which go inside of here. So let's go ahead and start that. So first thing we're going to talk about is current. So what exactly is current? So current then is if I have something like a wire. So let's say here's my wire. What we do then is we consider a cross-sectional area of this wire. So let's cut out some cross-sectional area. Then we're going to look at the number of charged particles which pass through this cross-sectional area in a given amount of time of, say, delta t. So each one of these guys has a charge. Let's call that little q. So over some macroscopic time frame, let's call that delta t, we're simply going to measure the total number of charges which pass through this cross-sectional area. Okay. So what current then is equal to the number of charge carriers within this certain amount of time of delta t. Okay. So this then we're going to call the change in charge divided then by the change in time, where my change in charge then is going to be equal to the total number of charges times the charge of each charge, where all of the charge carriers will have exactly the same number of, or the same amount of charge, I should say. So this is simply the number of charge carriers, carriers, 2 R's or 1 R, 2 R's, carriers, there we go. And then this is the charge of the charge carrier. Now, in those cases, charge of charge carrier. In those cases, this is just going to be the fundamental charge, which means this is just going to be E in most cases. Now, again, this is some macroscopic time frame, which means this is going to be like 1 second, 2 seconds, 3 seconds. So it's the total number of charges which pass through. Now, again, since a large time period, this is then equal to the average currents. So this is the amount or the average amount of charges which pass through this cross-sectional area in a given amount of time. So those guys actually are average currents. Okay. Now, does that mean that it's the instantaneous amount of charge which passes through this thing? So is it always the same? So meaning if I'm looking at 0.0 second intervals, for example, am I always going to have the same number of charges passing through this cross-section? Probably not, right? So in this case, we can define what's known as the instantaneous current, where instantaneous current then is the limit as delta t goes to 0 of our average current, which is the same thing as the limit delta t goes to 0 of our change in charge divided by the change in time. But what's the limit of a delta over delta? The derivative, right? So this is the time rate of change of the charge. So this is my dq dt. So what this says then is that the instantaneous current is actually the time rate of change of the charge, again, passing through this cross-sectional area. Okay? Now let's talk about units on this thing. So this thing has units of coulombs per second. This thing also has units of coulombs per second. A coulomb per second has a special name. This is what we call capital A, where capital A is what's known as an amp. This is also the same. So the units of current are amps, which is the coulomb per second. So it's how many charges pass through in a given amount of time. Okay? So this is current. So again, all we're doing with current is I would put basically an ammeter here, and I would measure the total number of charges which pass through as a given amount of time. Take that, and then give me the current itself. Okay? So next off, we have resistance. So let's talk about resistance. So depending on the strength of the battery, so in this case, for example, let me put the resistance to something reasonable. So we can see in this case then is what? If I look at my number of amps I have here, so I went to negative voltage, go to positive voltage. There we go. So if I have a small amount of voltage, in this case 1.2, I have a small amount of current. But then if I increase the amount of potential, I then also increase the amount of current. Okay. So in this case, let's go back to what I have. Let's say I have, I don't know, 1.44. I have an amperage of, I don't know, that doesn't give me a number, so that's not helpful, but it's less than, what's that, 10, 20, 30, 40, 50. So that's maybe around 4 amps. Okay, based off this diagram. So now if I increase this to, say, almost 7, I'm now going to be close to 20 amps in this case, right? So basically, if I make a plot of my current versus my potential, or my potential versus my current, what we find is that there's actually a linear relationship between the two. So as I increase the potential, I also increase the current proportionally. Or if I increase then the current, I also increase the potential linearly. So these guys are linearly proportional to each other. So this is, D then is going to be proportional to the current. So the amount of potential is proportional to the current. So as I increase the current, I increase the potential linearly. And if I increase the potential, I also increase the current linearly. Okay? The slope of this line is what's known as the resistance. So let's talk about this. So this brings us up to what's known as Ohm's good idea. It's technically a law, but I'm going to call it a good idea because it only works for one scenario and one scenario only, which is metals. If it's not a conductor, this doesn't work anymore. For example, if I'm dealing with something like a diode, the potential is actually proportional to the current squared, which is certainly not Ohm's law, right? So Ohm's law, or again, what I'm going to call Ohm's good idea, and in this case, I'll put in parentheses, only a law for conductors, says that our potential then is equal to the current times the resistance. This is Ohm's good idea, or Ohm's good law for conductors. Okay. So let's say that we now have this new quantity, resistance, where resistance is defined then as the current, or sorry, the potential per current. So this guy then is going to have units of voltage, so that's a volt, per amp, which is the same thing then as a volt second per coulomb. Okay, so remember an amp, not an amp. An amp is a coulomb per second. So this guy goes up. This guy gets a special name. This guy is what's known as a capital omega, which is what's known as an ohm, after Ohm's good idea. So this is resistance. The resistance then is the linear relationship between, again, in a conductor, the potential and the current. Okay, so again, these guys are linearly proportional. So as one increases, the other one increases by a multiplicative factor, which is that what we call the resistance. Right. So first thing to point out is what controls current? Is it potential or is it resistance? What controls current? Not potential. Potential is part of it, but it's actually the resistance, right? Because if I keep a fixed amount of potential, but if I massively increase the resistance, current is going to massively drop. Mm-hmm. And if I decrease the resistance, then the current is going to massively increase. So if you see something that has a particular potential, it's not potential that kills you, it's current, and the current is only controlled by the resistance, which means that if you saw 10,000 volts, that doesn't necessarily mean you're going to die if you touch it, because it's going to depend on the resistance of your own body, which is why some people can, play with, let's say 120 volts or whatever, which is typically in your house, and they can lick them and they can do all this stuff and they don't get fried. They don't get zapped at all because their natural resistance of their body is very high. Mm-hmm. So ultimately what kills you is not potential, it's current, which is dictated by the amount of resistance that you have. So if you have a big amount of resistance, you're going to have a small amount of current for a fixed amount of potential. If you have a small resistance, then you have a big amount of current, which could kill you. Next question. How much current does it take to kill a person? Not too much, but not like a lot. Well, current is independent of this. Because I'm only talking about the current, but you're right. It turns out to be the resistance, but I'm saying independent of the resistance, how much current would it actually take to kill you? That's a better question. Let's say assume a normal, healthy person. It's 100 amps. Exactly. So 100 amps of current through your heart is enough to kill you. What's that? It's 100 amps. Well, plus or minus depending on the person. Okay. Yeah. Yeah. Good question. We'll get to that in a second. But yeah, what determines? A lot of it has to do with how much water that you dictate, the density of your muscles, the density of your bones. There's a lot of factors that go into those things. So, but yeah, some people have natural high ones because they have denser bones. They also have like thicker muscles. They have less body fat. They have less water. So those are all things that will carry current differently, which also determines their overall resistance. But yeah, there's a lot of factors that are going to go into that. But I would suggest don't try it. That'd be great. Everyone's okay. So this is what we call resistance. So again, resistance is what actually controls the current, not the potential. So that's kind of a misconception that most people have, but it's the resistance that controls the current, not the potential. So let's talk about another way we can view resistance. We kind of talked about this in the lab. I'm going to talk about it again. But if we look at the microscopic version, so this is our microscopic version, where the other one was the macroscopic version. So let's look at the microscopic version. What we said in the lab, and we're going to repeat it here, is that when I apply a potential difference to this, so here's my potential difference, that's going to create an electric field, where that electric field is going to point in this direction. Okay? Now, if I take a positive charged particle, even though it's actually negative charged particles, but let's pretend, this thing, as we just said, is going to feel a force. That force then is going to point in this direction, the electric force, which means this guy then is going to try to accelerate across. But again, as we mentioned in the lab, as this guy is trying to accelerate, and also at the beginning, it's going to make elastic collisions, causing this thing to basically bounce around, trying to go from one side to the other side. Looks like Planko, if you guys are familiar with Planko. So what this means then is we can view resistance then as the energy which is taken away due to these collisions. Okay. So ultimately, the microscopic version says that the charge carriers are making elastic collisions causing them to speed up and slow down all the time. So anytime this guy makes an elastic collision, it's going to bounce off, which means it has a force pushing back in this direction. But then the electric field is going to kick over and try to accelerate it in this direction again. Right? And then it's going to make another elastic collision, giving it a force in the other direction. But then the electric field is going to try to accelerate it. So ultimately, it's going to move down here, but it's going to do it very slowly. Right? So again, what we imagine that current in then is the average velocity at which these guys move across. So this is our average velocity, which is also what's known as the drift velocity. And we'll come back to this later. So this is our drift velocity. But basically what this thing says then is we can think of current directly proportional to this drift velocity. So current then, again, is the amount or the average velocity that these guys have as it moves across from one side to the other side. Okay? And again, I'll prove these things to you later. So what we can view then as resistance is what I call the probability of death. Probability of death. Or you can think of it as the probability of a collision across the thing. But I like the death one better. So let's talk about that one. So this is going to be our mental picture to kind of talk about this. So let's say, have you ever seen the first Saw movie? I know that was like 150,000 years ago as far as you guys are concerned, but anybody see the first one? No. So there's a scene in there where one of Jigsaw's traps was that this poor bastard standing over here had to crawl across this razor wire trap. So this thing had razor wire all crossed on the inside, and he had to make it from this side to this side, and if he made it to this side, he lived. Okay. This is basically the trap. So this is all razor wire. He has to go from one side to the other side. So we're going to use this to determine what is the resistance, which again is directly related to this probability of death. So we want to see what factors go into this that's going to increase his probability of death. Is this poor staff actually going to die before he makes it across? Okay. So what factors do we have? We have this guy here, which is the length, how long this thing is. We have the cross-sectional area, and we also have the density. So rho. So you can think of rho, at least for now, as the density. So the density of the wires. Okay. Rho is actually going to be called what's called resistivity, but you can think of it for now as the density. So let's think of this probability of death. Let's call that R. This is our probability of death. And let's examine each one of these factors at a time. So if I increase the density of these razor wires, what happens to his probability of death? Is he going to die, or is he might have a chance to live? He's going to die, right? So his probability of death then has to go up, right? If I increase that density, he's got nowhere to kind of slither his way through, which means he's going to get ripped apart. His stomach's going to get ripped wide open. He's going to have bile and stuff come out, right? He's going to die. Not to get overly graphic, but it's kind of fun. Okay? Now, let's think about this one. The length. If I increase the length of this, let's say while holding the density constant, and if I increase the length, is he going to die or is he going to make it? Is likelihood going to be higher for dying or lower for dying? Higher for dying, right? So the longer I make this thing, his probability is going to go up, right? What about, finally, the cross-sectional area? So let's say this is made out of 10 razor wires, still has the same length, but now I'm going to increase the cross-sectional area. Is his probability going to go up or is it going to go down? So basically meaning that, does he have a little tunnel like this to crawl through? Or does he have a big tunnel like this to crawl through? Is it going to go up or down? What's that? It's going to go down, right? So it's going to go down because he can find more ways to kind of slither through this 10 razor wires. All right, so he has a lower probability of death. Right? Or the other way you can think about it is I'm sending an electron through or charged particle through. So it's the probability then of making a collision. Okay. So the more density I have, highly packed as these guys are, the higher the chance of a collision. So the probability goes up. The longer it is, the probability goes up. But if I get cross-sectional area getting bigger, has more room to kind of wiggle its way around, so the probability goes down. Right? Don't think about it that way. But I like the death one better. It's more fun. All right. So put these things together. What this thing tells us then is that resistance on a microscopic level, because that's what we're talking about here, is then going to be equal to this rho times L over A. Where again, L here is the length of the resistor. A is the cross-sectional area. And then finally, rho here is what we're going to call the resistivity. So you can think of it again as density, but it's what's called the resistivity. So rho here, which is equal to our resistivity. This guy is actually a property of the material. So meaning things like gold, copper, tungsten, whatever type of material that it is I'm looking at, nichrome like we played in lab, all are going to have different resistivity to them. So it's a property of the type of material that it is that I'm actually looking at. And to make it more fun, is it's actually temperature dependent. So this guy here is actually temperature dependent. So meaning as the temperature goes up, the resistance changes because the resistivity changes, which means the current changes. Something we kind of talked about last semester when we talked about different types of thermometers. This was important for when it came to resistive thermometers, right? Ones that you had electric that you put in your mouth and measure the change in temperature of the resistor, which corresponded then to a particular temperature. Okay? So the way this guy is dependent on temperature is this guy's going to be a rho zero, where rho zero then is the resistivity at some reference temperature. So at a temperature of T is equal to T0. All right. So this is going to be the same thing then as what? The resistivity times 1 plus alpha times my change in temperature. Right. Hey, Graham. So what's alpha? Alpha is a new constant. So alpha is what's known as, what is alpha called? So I give you the right numbers and stuff here. Did I write it down? Of course I didn't write it down. Why did I do something smart like that? So this is something like the linear coefficient of resistivity. Or yeah, resistivity. I believe that's what it's called. I could be wrong on that. I'll fix that next time if I have that wrong. But this thing has to have units of what? 1 over temperature. Right? Okay with that? So this thing then has units of 1 over Celsius, which is equal then to 1 over Kelvin. Now, again, this is just going to be a number, which is then, again, material dependence. I just heard a whir in my ears, which I think the sound doesn't work on there anymore. And my microphone doesn't work, so that's okay. So yeah, if you watch the video, then you won't have sound from here on out. So it's gonna be great. Or the right? So not too bad. So anyways, this means that our resistance then is also temperature dependent, where the temperature dependence of the resistance then is going to be equal to the resistance at, again, this reference temperature. So this is at T is equal to 0 times then 1 plus alpha times the delta T. So this is our temperature dependence of our resistance. Okay? So again, all this means then is what? As the temperature goes up, the resistance goes up, which means as the resistance goes up, what happens to the current? It has to go down, right? If I decrease the temperature, in that case, the resistance goes down and the current then has to go up. Okay? So this is then the microscopic version of resistance, or the microscopic version of resistance is simply that what we have resistance is equal to the resistivity, which again is simply a number, times the length divided then by the cross-sectional area. So cool. So let's use all this and let's do a quick example. Get my plug here. Yeah, plenty of that. So this one says that suppose you want to connect your stereos to speakers by using a wire. And it says if the wire that you use is 20 meters long, wants to know what diameter copper wire should be used to keep the resistance less than 0.1 ohms per wire. Okay, so let's talk about this. What's your picture? So let's say here is my stereo. And then here is my speaker. And there that is a stereo. And this is my speaker. And when I connect these guys together by some wire, where the length of this wire is equal to 20 meters. Okay. Now, what we want in this case, again, is that the resistance of the wire is, say, 0.1 ohms. So we're going to use it as 0.1 ohms because we want it to be less than air. So this is the biggest diameter that we can have. We'll think about it that way. So in this case, we want to know, we want our resistance to equal 0.1 ohms. What it ultimately wants me to do then is if I look at the wire, right, my wire is going to be a cylinder. So it wants to know what diameter of my cylinder do I have to use. So what diameter of the cylinder will make this at 0.1 ohms if it has this particular length to it? We doing okay? So what do we know? We now know this guy here. So we now know that's what resistance is equal to resistivity times the length divided by the cross-sectional area. Now, if I'm dealing with a cylinder, what kind of shape is the cross-sectional area? A circle, right? So in this case, my area would be equal to pi r squared, but I want the diameter. So how is the radius related to the diameter? Half, right? So I know the radius is half the diameter. So it's going to be the same thing then as pi times the diameter squared divided by 4. Okay? So let's plug that in. So this guy's going to be the same thing as 4 times the resistivity times the length divided by pi times the diameter squared. Okay? So from here, I just want to solve for the diameter. So I'm going to cross multiply. So I'm going to get my diameter squared then is equal to 4 rho L over pi r. And then finally take a square root. So this is then going to be my diameter. So it's going to be the same thing as 4 times the resistivity times the length divided by the pi times the resistance. Okay. So let's put on our numbers. So it's going to be 4. Did I write down the resistivity of copper? Probably didn't. Oh, yeah, I did. Okay. So it turns out the resistivity of copper is equal to 1.68 times 10 to the minus 8. And this has units of, going back to here, so since this bidimensional analysis has to be an ohm, this is a length over an area, so that's a per meter. So this thing then has to have units of ohm meters. Okay, so resistivity here has units of ohm meters. So this guy's going to be an ohm meter. So good, so let's put that in. So times 1.68 times 10 to the minus 8 ohm meters times the length, which is 20 meters, divided then by pi times the resistivity, which is 0.1 ohms square root. So what are my numbers? What I get in this case then is my diameter turns out to be 2.02 millimeters. So this is my diameter. Okay. And of course, that corresponds to the gauge of the wire. This is when we talk about gauges. Different gauges have different cross-sectional areas, which determine the amount of resistance that it has. Okay. So next part is part B says, so each speaker is to have 4 amps of current running through the wire, and it wants to know what is the potential difference or the voltage drop across the wire. Okay, so now we know is that our potential difference across here is what we're looking for. So what is this V? And we know that this guy's going to have a current running through here, where that current then is equal to, what is this, 4 amps. I just realized I didn't talk something about current, so we'll go back to current here in a second before I do microscopic version of current. So in this case, what do we know? We know the resistance, we know the current, and we want the potential. So whose good idea should we use? Ohm's good idea, right? So Ohm's good idea says that the potential then is simply equal to the current times the resistance. So this is going to be our 4 amps times 0.1 ohms, which is the same thing as 0.4 ohms. So our potential drop across our wires here is 0.4. Nice and easy. Okay? Now let me go back to current because I just realized, again, I forgot to talk about something with current. So let's talk about current here for a second. So one thing to note about current is current has a direction, but it's a scalar quantity. So even though current flows in a direction, it's defined as a scalar. Right. So what does that mean? So that means is, let's say I have a node, right? So I have one wire coming in, and then I'm going to have 2 wires leaving, which is going to create my node. So I have something like this. So this is my node, or my junction, as we're going to call it. So this is a node / junction, which means the current can separate, right? So let's say in this case, I have current flowing in this direction. Let me just call that I. And then by the time it gets here, it's going to split into 2 pieces, right? So I'm going to have some currents going in this direction. Let's call that I1. And I'm going to have some current flowing in this direction. Let's call that, use a different color. There we go. Let's call this guy I2. Now, what has to be true is that the current coming in has to equal the current coming out. Now, because current is not a vectorial quantity, that means I don't have to worry about angles, right? So when I add these guys together, it's not a vectorial sum because now it's just a scalar sum because the way that we've defined this then is as a scalar quantity itself. Okay? So unlike electric fields where we would have to worry about directions, right? So we'd have to look at angles and all that different stuff. In this case, we don't have to because it's simply a scalar quantity. So what this says then is what's by charge conservation, which we're also going to call conservation of current, even though it's exactly the same thing, says that's what my current coming in, I, has to be equal to I1 plus I2. Okay? So in this case, again, whenever I'm dealing with current, since it's a scalar quantity, I don't have to vectorially add these together. They're simply just going to be added together. Okay? Now, this brings up stuff to, again, conservation of charge or conservation of current, which says at a junction, i.e. a node, we have to have that the sum of the currents coming in must be equal to the sum of the currents coming out. So what does this mean? This means that I can never only have currents coming in, or I can never only have currents going out. Okay. So what that means then is that a given junction, I couldn't have, say, all possible currents coming into one location. So I couldn't have, say, I1 coming in this way, I2 coming in this way, or I3, say, coming in this way. This is not allowed. Okay. And why is that true? From a physical standpoint. Exactly, it's gonna blow up, right? Gonna catch fire, this thing is gonna be bad, right? And I simultaneously can't have, if this was my junction, I couldn't have I1 leaving, and I couldn't have I2 leaving, and I couldn't also have I3 leaving, right? This is also impossible. Okay? So it has to be true that at any junction, the number of currents coming in has to be equal to the number of currents coming out. Okay, so in this case, what's coming in is I, what's leaving is I1 and I2. Okay, so this is something. So next thing we want to talk about is the difference between macroscopic currents and microscopic currents. So the current we talked about so far is macroscopic, which means that we're taking the wire in this case, or whatever our resistor is here, and we're simply looking at the total of the cross-sectional area, the number of charges which pass through the total cross-sectional area, right? Which means that the current which is passing through this thing is actually the weighted average over the entire cross-sectional area. Now, does that tell me how the charges are actually moving from location to location to location inside of the wire? No. So this is going to bring us to the microscopic version of current, which is what's known as current density. So let's talk about some current density here. So the current density is the microscopic version of the currents. So this is what's going to tell us what is actually happening inside of the wire. So this will give us our location dependence number of charges moving through the wire. So what does that mean? So that means that, for example, inside of this wire, it could be that we have more charges moving at the center than we do as it goes toward the outside. So as it goes to the outside, this thing is going to taper off until maybe at the complete outside, I have zero curves or zero number of charges passing through. This is an example. Or it could be, I would have the complete opposite. I could have that I have maximum number of charges moving through at the top portion. And then as I go to the center, it could taper off this way as well until eventually I get to the center where I have no charges actually moving through. Or it could be that it's constant everywhere through. So at every location, this guy is constant, right? So ultimately, what my current density then tells me is the profile of how the charges are moving through the actual resistor or wire itself. Okay, so it's telling me in this case, I have a lot more running through the middle than I do on the way outside, or I have a lot more on the outside than going to the middle, or it's constant all the way through. Okay, so these lines that I'm writing down here are what are known as the current density, which is called J. So J is actually a vector which represents the current per unit area. So this is what we call current density. So the current density is then going to be equal to, at least this is going to have units of amps per meter squared. So that's the units of this guy. And then, we're okay. So how does current density then relate to the actual current itself? Well, they're related by the fact that what? The current is the weighted average of the current density over the entirety of the cross-sectional area of the wire. Okay, which means that my current, in terms of current density, is equal to the integral of the current density dotted by the differential area. This is our definition of the current density. Okay. Now, in this case, if our current density is equal to a constant, then this guy is simply going to be equal to the current per unit area. So in this case, my current density would be equal to the current per unit area if it's constant. If it's not constant, then we have to know the functional form of this guy. Okay. So this is what we call the current density. So again, in general, my current density is actually going to be a function of position, where we would have to know the functional form of this. But again, it's going to tell me as I move outward, my current density gets smaller, or as I move outward, it gets bigger. Right? Or it's constant all the way through, right? Whatever that happens to be. This is what we call current density. Again, this is the microscopic version of current, which is the position dependent or the location dependent representation of what's actually happening inside of the wire itself. Okay with this? So let's do some examples of this. Let's see how this guy works. So let's say that we have a wire which has a radius of 3.4 millimeters. And if the magnitude of the current density is given this way, so for part A, it's going to be what? J times R, which is the position dependence. So R in this case is going to be the radius away from the central axis. So in this case, this is going to be my R in this direction. And then capital R in this case is going to be the radius of the wire. So this is my capital R. So this is just saying it's some constant J0, where J0 is equal to 5.5 times 10 to the fourth amps per meter squared. And then the profile looks like this. So it linearly grows. So that's actually part A here. This guy's linearly growing on the inside. So this is actually part A. And then part B is going to be that same constant J0, but now 1 minus this guy. So R over R0, which means at 0, this thing has maximum. And as R goes bigger to eventually becomes capital R, it's going to go to 0. So that's actually this picture. So this is B. So it wants me then to determine the current for those two different wires with those two different cross-sectional areas. All right. So let's talk about this. So we now know that what? The current is equal to the weighted average of the current density dotted by dA, where dA again is a vector which points perpendicular to the cross-sectional area. Okay with this? Now let's take in this case. So since my current density is moving horizontally, this means that the dA that we want to choose will also be pointing horizontally. Okay? So that way our dot product between the two just gives me 1. Okay? So the way we're going to do this is because this thing is R dependent, we're going to take this cross-sectional area here and we're going to chop it up into a bunch of rings, just like we did before. Okay? Where each one of these rings is going to be at a radius of R, and it's going to have a thickness of dr. Same things that we did all those thousands of years ago now. Okay? So this means that the magnitude of my dA will be, for our purposes, always 2 pi r dr. Now, as far as this class is concerned, this will always be true. This will be true. We're only going to consider wires. It can get more complicated, but let's not worry about that. Everyone's okay? Which time? Oh, yeah, 1 minute. Okay. So basically, we'll take this up next time, but this means then that our current is going to be the same thing as 2 pi times the integral of the current density times r dr. Okay? Where our bounds of integration in this case, of course, is going to be from 0 to capital R. So I'll pick up with this tomorrow because I am officially out of time. You see my phone? Oh, I left it over there. That was useful. So anyway, so yeah, we'll just use those two different ones, plug them into the integrals, and then talk about it, and then call it a day. That was okay. I know that was a lot today. I feel like I talked really quick today. I'm just super excited. All right, no questions. All right, do свидания. Auf Wiedersehen. Tschüss. Arrivederci. Ciao.
Oh, they were bad.
That's better than what mine were. So I just bought a car a few weeks ago. We had to drive it back from Cincinnati.
Oh,
By the time I got home, I had 22 PSI. And it started off at like 41.
yeah.
So it drained a lot. And then by the time I got up the next day, I had 9.
Oh, wow.
9.
Yeah. But bad. I had to fix that this morning. Like,
Gotcha.
first driving wonky and it's not right.
Oh, yeah. Well, every car does, yeah. So.
My picture